Well, before you get all excited, this is not the real-life kind of inequalities, as in protesting systemic injustice inequalities. This is the math kind of inequality, as in how do I find out what values of x make, say, 4x plus 5 bigger than 3x plus 2. So it's like an equation, except one side is bigger than the other, and we're going to work on solving these today. It turns out that keeping the balance turns one true statement into another true statement. So for example, I could subtract 3x from each side, just like if it were an equation. And that tells me that x plus 5 is bigger than 2. And then I could subtract 5 from each side. And I get x is bigger than negative 3. So as long as x is bigger than negative 3, 4x plus 5 will be bigger than 3x plus 2. So it's almost the same as solving a linear equation. There is one big difference, though, and that's I can say 2 is less than 4, right? If you're having trouble remembering which way these are supposed to point, the way I learned it in second grade that I've never forgotten is that the alligator eats the bigger number. So here x is bigger than negative 3, here 4 is bigger than 2. So I can say 2 is less than 4. If I want, I could add 1 to each side and say 3 is less than 5. If one is true, then the other will be true. I could multiply both sides by 2 to get another true statement. So I'm keeping the balance. 6 is less than 10. That's also true. 6 is less than 10. But here's one thing that's a problem. If I multiply or divide by a negative number, let's say I divide by negative 2. The problem with multiplying or dividing by a negative number is that then I would get negative 3 here and negative 5 here. So think of it this way. 2 is less than 4, here's 2, and here's 4. And 2 really is less than 4 because it's to the left. So when I add 1 to each side, I'm really just moving this whole number line over. Now it says 3 is less than 5. I moved them both 1 unit to the right, and so 3 is still to the left of 5. And when I multiplied by 2, that's like stretching this whole number line out because 3 gets twice as far away from 0. Here's 0, here's 0. 5 gets twice as far away from 0. So 6 is still to the left of 10. But when you multiply or divide by a negative number, that's like flipping this whole thing over. 6 was to the left of 10, but negative 3 is to the right of negative 5. So when I multiply by a negative number, going from 3 is to the left of 5 to flip that whole thing over, negative 3 is to the right of negative 5. So if you multiply or divide by a negative number, then you have to flip the inequality sign. So that's anytime you multiply or divide by a negative number. Adding or subtracting a negative number is fine, but when you multiply or divide, it's like the whole number line flips over. So anything that was to the left is now to the right and vice versa. Otherwise, other than that one detail, inequalities work just the same as equations. So let's see another example where this comes up. Let's say I was told that negative 6x plus 4 is less than 34. And I want to know what values of x can I plug in to make this expression strictly smaller than 34? To find out, I could subtract 4 from each side. So that doesn't change anything. I'm moving the whole number line to the left. Now negative 6x has to be less than 30. But check this out. When I divide by -6, I get x here and 5 here, but I have to flip the inequality sign over. So x here and 5 here, the inequality sign has to flip to looking this way. So make sure you remember that flip right there. Let's take a look on the number line and see why this is true. So our solution is x is any number bigger than 5. So this is saying -6x plus 4 has to be to the left of 34. So it can be any number smaller than 34, any of these numbers. But this is saying x has to be to the right of 5. So that's any of these numbers. So let's take some looks. For example, if x is 7, that's to the right of 5. So here's 7. Here's 7. Man, Google Meet is especially slow today. When x is 7, -6x plus 4 is equal to, whoops, that should be a -5, shouldn't it? So when x is 7, -6x plus 4 is equal to -6 times 7 plus 4, so -38. That really is less than 34. Or let's go right up next to it. When x is -4, -6x plus 4, that's equal to 24 plus 4, that's 28, and that's still less than 34. But if I make x less than -5, if I plug in like x equals -6, then -6x plus 4, that's equal to 36 plus 4, and that's 40, which is not less than 34. So whenever x is to the right of -5, like these numbers, we're fine, but when x is to the left of -5, we're not fine. So that's some empirical evidence that we really do want this side of -5 and not that side. And that's what happens when you multiply or divide by a negative number. The side you're looking at has to change because the whole number line flips over like we saw in the last example. Let me do another inequality. Whoops, don't need a number line right now. I'm going to draw a number line in a second. I'm going to talk about 3 different ways to represent your answers to see what interval notation is. So let's say you told me that 2x plus 3 was greater than or equal to 5. And here's the difference between this symbol and those. This is greater than or equal to, whereas this just means greater than. So if I said, I could say 6 is bigger than 5, or I could say 6 is bigger than or equal to 5. The difference is that I could say 5 is greater than or equal to 5. 5 is at least as big as 5. The only one I can't say is if I write this, 5 is bigger than 5. That is not true. So I'm going to cross that one out. So this says 6 is bigger than 5. This one says 6 is at least as big as 5. 5 is at least as big as 5. That's true. But 5 is not strictly bigger than 5. So that's the difference between these two symbols. So this one says if 2x plus 3 is 5, that works. If 2x plus 3 is 5.1, that works too. But up above here, when I say x is big -5, that means -4 works, -4.9 works, -4.99999 works, but -5 doesn't work. So there isn't a smallest number that works, which is a little bit counterintuitive. You can always find a smaller number that works. That's how these two symbols are fundamentally different from each other. Here, there's going to be a small value of x that works. So I can subtract 3 from each side and get 2x is at least as big as 2. And then I can divide by 2. X is at least as big as 1. I don't have to flip the sign because I'm dividing by a positive number. So x could be 1, then I would get 2 times 1 plus 3 is exactly 5. Or it could be 1.00001, and then I'd get 5.00002 is bigger than 5. Or x could be 2 or 12 or 17 or 10 billion and 6 or a googolplex. It can be any number as long as it's bigger than 1. On a number line, I might write that like this. Here's 0, here's 1. And the way I'm going to draw it is I'll fill in a circle at 1. So x could be, there it goes. And then I'm going to shade in all of the numbers bigger than 1 all the way up to this arrowhead. And that's arrowhead is going to represent that any number bigger than 1, no matter how far to the right we go, works. But there's another notation that's easier than writing an inequality or drawing a number line, and that's called interval notation. So let's say that I wanted to talk about the numbers, where the number is going to be bigger than 3, but it's going to be no bigger than 6. So bigger than 3, not any bigger than 6. On a number line, the way I draw this is, let's say here's 0, here's 3, and here's 6. X can be any number as long as it's bigger than 3, so it can't be 3. So we're going to say and. These have to both be true. And means both are true, or means either one is true, right? So it has to be bigger than 3. I'm going to put an open circle right there. A 3 doesn't count, but anything bigger than 3 counts. And that's because there's no smallest number that works. So 4 works, 3.5 works, 3 1/4 works, 3 1/8 works, 3 1/16 works, and so on forever. It's just 3 itself doesn't work. So 3.00001 works, but no matter what number you pick down here, there's always a smaller number that still works. You can always, it's like limbo. You can duck between whatever number I put my cursor on in 3. Right? You could take the average of that number in 3, and that would work. But on the other side, 6 is the biggest number that works. There's no bigger number that works. X can be 6 or anything smaller. So this is how I would draw the interval. But what I've got is something called interval notation. And it's really intuitive. All I have to do is say the smallest number that works is 3. The biggest number that works is 6. And then there's 2 ways I can draw the borders. I'm going to put these inside a grouping symbol. And the way that's going to look is the 3 gets a parenthesis, and the 6 gets a bracket. So if I have an equality bar, then a closed dot and a bracket. If I have a strict inequality, then I draw an open circle and a parenthesis. So those are the triplets of symbols that go together. So that's just how we translate this to interval notation. That's the symbol they picked. So this says starting at 3, but not including 3, going up to 6 and including 6, and any number in between. And that's all the numbers x that work. Okay? Ooh, gross. Oh, there's a really big tick on my notes, class. Oh, that's so disgusting. Let me take care of that real quick. Where is... Haha, good news, class. The tick is now on fire and the notes are only slightly singed. Whew, close call. Summer in Georgia, gotta love it. Okay. Okay, the notes are more than slightly singed. There's a hole in the notes, but it was worth it. I can still tell what I was about to say, and what I was about to say was, let's take a look at the solution to the previous problem. Do you smell that? Burning tick. So in the previous problem, I said x could be any number bigger than 1 here. So I said x was number bigger than or equal to 1. It could be 1 or any number bigger than 1. On a number line, that's going to look like this. Here's 1, and I said we fill in a closed circle for 1. Let me check my legs real quick and make sure no more jumped onto me. I was outside a little bit ago. I was foraging for berries in the woods. Nope, looks like that was the only one. No idea how it got on my notes. Okay, so I need an interval to represent this. This is one unbroken line, so I can represent it with an interval. I'm going to start at 1, and 1's included, so it gets a bracket. But then there's no stopping point. So in this class, I want to be very clear that infinity is not a number. I can't do mathematics with infinity. Like, there's no consistent way to say add, subtract, multiply, or divide by infinity. So it's not that kind of number. Rather, it's a symbol for that end of the number line. And negative infinity is a symbol for this end of the number line. So I'm going to use that symbol in interval notation and say, there's no stopping. We're going to go all the way up to infinity. But then if I put a bracket, that would say include infinity, and that would be like infinity was a number. Infinity is not a number, it's a concept, and so I can't include it like a number. I just have to put a parenthesis here to say any number smaller than infinity works. Does that make sense? Like this says any number bigger than 3, and this says any number up to and including 6. This says any number 1 or bigger, and this says any number smaller than infinity. And since every number is smaller than infinity, this just says any number bigger than 1, full stop. I don't have to say smaller than infinity because that's all of them. So that's how we write that in interval notation. And I think, let's take a look at a few more. If I wanted to talk about, let's draw a few and then look at how they look in interval notation. Let's say this is -2 and this is 5. Those are both closed dots, so this is any number at least as big as -2 and no bigger than 5. So the interval would look like this, 2 brackets. Where it can get a little confusing is if I said it has to be bigger than 0, but it has to be smaller than 10. So 0 and 10, not including 0, not including 10. So I would draw that like this, open circles on anything in between. So this is a set that doesn't have a smallest number and doesn't have a biggest number. The way I would write this is like this. Only problem is this kind of looks like a point on a Cartesian plane. This is not a point, but I will always make it clear to you through context whether I mean a point or an interval. So we have to tell from context that this represents an interval and not a point. So that's one place where this notation gets a little confusing, and I apologize, but this is the standard notation in the field, so this is the one we're going to learn. Let's say I said any number smaller than 3. On a number line, I would say here's 3, and I said smaller than 3. I didn't say 3 was allowed. 3 is not smaller than 3. So I'm going to put an open circle here. So 2.9999 would work, but 3 doesn't work. And then I'm going to shade in all of the numbers below. And so the way I would write that as an interval is like this, -infinity up to 3. They both get parentheses. 3 gets a parenthesis because it's not included. -infinity gets a parenthesis because infinity isn't a number. Okay, so that's interval notation. We'll talk a lot more about it when we get to functions and their domains and ranges, if you've heard those words before. Ooh, one more interval for you. What if I say any number works? Can you think of what interval that would be? You could try drawing a number line to help you. Any number works. So no matter how small the number is, and no matter how big the number is, it's going to be just fine. The way I'll write the interval is anything bigger than -infinity and anything smaller than infinity. And that's just every number. So negative infinity to infinity is interval notation for all real numbers. In fact, we have another symbol for this set. You could use this interval notation for the set, or if you just want to say it as all real numbers, so that's every number that isn't a complex number, then another way we could write that is in R with 2 downstrokes, like this. This is the symbol for all real numbers if you want to be writing less than the interval. So either one of these is perfectly fine, except sometimes on MyOpenMath it only takes this one. So either way. Okay. Woo, heck, that's a that's a fancy. All right, my next example is a little bit extravagant. It says x plus 1 over 3 minus 2x minus 4 over 6 is less than or equal to negative x over 2. Now, I want to show you 2 solutions to this one because the way that I prefer to solve it is a little bit fast and it makes some people uncomfortable. So I want to show you a slower way and then a faster way. So pick the speed that you're most comfortable with. Either way, we have to get rid of these awful fractions. We have to get a common denominator to even start comparing these. So I could say the least common multiple, this is the slow way, of 3, 6, and 2 is 6. That's a multiple of all of those. So that's going to be our common denominator. And so to get a common denominator, I'll multiply the first thing by 2 over 2. I'll multiply the second thing by nothing. It's already got a denominator of 6. And I'll multiply the third thing by 3 over 3. That way all of my denominators will be 6. Now be careful to distribute that 2. This will say 2x plus 2 over 6. This will say 2x minus 4 over 6. And this will say negative 3x over 6. And then we can just cancel out that common denominator. So this would say 2x plus 2. Now what do I need here? This entire fraction, both terms of the numerator, are subtracted. So when I cancel out the denominator, I have to give a grouping symbol to this fraction to keep it together. This giant fraction sign was the only thing grouping it, so now I need to write in parentheses, because this whole 2-term expression is being subtracted from this one. So I've canceled out the denominators, and now I can combine like terms. 2 minus negative 4 is 6, 2x minus 2x is nothing. And now, when I divide by a negative number, oh gosh, by far the worst point of finding one tick is that every little tickle on one of your body hairs after that feels like a tick. This is the worst. I'm like checking my feet and legs 5 times a second. So it's like, is that a tick? Is that a tick? I do not want Lyme disease, class. But the berries are so delicious. I have to forage. Saw a turtle today. Anyway, I have to flip this sign, and negative 2 is bigger than x. Once you have some practice, you'll be able to go from inequalities straight to interval notation without drawing a number line first. So do that as soon as you're comfortable with it, because that's the faster way, but I'll keep drawing this. Negative 2, shade in that dot because we're allowed to be equal. And so this interval, we always go from left to right in interval notation. I don't know if I said that before, but we always go from left to right. So this is the interval from negative infinity up to negative 2. Negative infinity always gets a parenthesis. This time, negative 2 gets a bracket because it's a closed circle. So I said this was kind of the slow way of doing things. And I specifically mean the first part. First, I got a common denominator by multiplication by fractions. So this is the nice, careful way of getting a common denominator. I multiply by 2 over 2 because multiplying by 1 doesn't change the value. Going backwards, these just cancel out to get the original equation. Well, original inequality. Going backwards, these just cancel out to get the original. So I haven't changed the value. It's not that I just kept the balance. I actually didn't change the value of any of the three terms from here all the way to here. The first time I changed the value of terms is in line 4. So there's a faster way to do things. The faster way to do things is, say, multiply both sides by 6. So this is the fast way. I'm going to write out, it's not going to feel fast because I'm going to write out every step, but I'll show you which steps I would skip if I were doing this on my own time. So I'm going to say 6 times the left side is less than or equal to 6 times the right side. Whole thing in parentheses. And now what I'm going to do is distribute the 6. So this first term is 6/3 times x plus 1. This second term is 6/6 times 2x minus 4. And this third term is -6/2 times x. Remember, denominators are just multiplying by the reciprocal. So you can always switch. You see how I slid these denominators to the left? You're always allowed to do that. Multiplication is commutative, and that means as long as you keep the top on top and the bottom on the bottom, you can write your fractions in whatever order you want. And I think that's the part where the fast way confuses people sometimes. Anyway, 6/3 is 2, 6/6 is 1, and -6/2 is -3. If I were doing this in my own notes, just with what I know of math, I would go straight from to this line. I would go straight from here to here because I'd say, all right, 6 is the biggest denominator. I'm going to multiply. Oh, there was another tick on me. Oh, gross. Ugh, sorry, class. Okay. I would say I'm multiplying both sides by 6. So this is 6/3 is 2. 6/6 is 1. 6/2 is 3. I would go straight from this line by multiplying every single term by 6, and that would be my first step. Okay, and then I would finish solving the problem as normal. So the rest of the solution is the same either way. It's just once you get used to these things, once you get used to fractions specifically, this method on the right will be faster for you than this method on the left. Because I don't have to be careful to preserve their values, I only have to preserve the balance. But you see, we end up in the same place. All right. And we got our solution. We wrote it in interval notation, so we're all done with this problem. Okay. Next things we're going to do are let's solve inequalities with the words and or. In fact, let's do this in a second part of this video.